States. Finally, he was graduated in Columbia University. And after that, in 1965, he obtained the PhD at Harvard University. Finally, he got a position at Cornell University. Right now, he's a chemical professor emeritus at Cornell University, and he's also human letter professor emeritus at Cornell University. Well, Roald Hoffman is member of the National Academy of Science, and he's also member of the American Academy of Art and Science of the United States, and he's also member of the American Philosophy Society. Roald has received more than 30 honoraris awards. Let's talk about one of them. He's the only person in the world receiving the American Society Award in 3 different subjects: organic chemistry, inorganic chemistry, and also in chemical organic. And of course, as you know, he received the Nobel Prize in 1991. Shared with Professor Fukui from Japan. Roald Hoffman has published more than 500 papers in science topics. And he is one of the most serious chemists for all science. Thanks to his work, he has provided to the scientific community a wonderful tool to understand and to investigate the geometry and reactivity in some molecules, in many molecules, coming from organic to inorganic, and also in infinitely standard systems. Well, Roald has also published a lot of books and poems, and which has been translated to different languages. This topic is related with the mixing of science and social science, and also mixing between science and philosophy. Today here, Roald is going to tell us about the chemical bond. He's going to explain about both experimental and theoretical criteria to decide when we have a bond and a strength of a bond. Just at the end of this talk, we will have some minutes to ask questions to Roald Hoffman. Please do not take photos during the talk. Take photos only before or after the talk. Por favor, por expresa petición de Roald, no tomar fotos durante la charla, solamente antes o al final de la charla. Please, do not forget to turn on your mobile phone when we finish here, because some of your family would like to call you when we go back home. Por favor, no olviden encender vuestros móviles cuando terminemos aquí. Es posible que algunos de sus familiares quieran llamarlo cuando estemos de vuelta a casa. So please, let's give a warm welcome to Professor Roald Hoffman. And thank you for coming.
Right.
Testing, 1, 2, 3, yes. Okay.
Turn off?
Yeah, turn off the light, please. Okay. No, it's okay.
Un segundito.
It's okay.
Un momento.
Yes, it'll work.
Vale.
Okay, thank you. Thank you. So please come in. There are some people there who are standing. I'm very glad to be here in Sevilla. And I want to give this lecture, which will last 2 hours, and there will be a 10-minute break in between after 1 hour. I want to thank the Plan de Investigación de la Universidad de Sevilla and the Escuela Politécnica for its support of these lectures. The second lecture will be about my childhood in wartime, Poland and Ukraine, and the third lecture will be a general one about a kind of philosophical problem that we have about the tension between simulation and understanding. I want to thank also Norge, who has visited our group, and I want to thank him for the invitation, but also for the transport that we have had here. This is... Now, let's talk about the chemical bond. So here are two quotations by two great figures in theoretical chemistry, Charles Coulson and Robert Mulliken. And you can read those as well as I can. The first comes from Charles Coulson, and it is actually, I think the microphone went off for a moment. Can you hear me in back? Is it all right? Yes. You can see from Charles Coulson from an after-dinner talk that he says that sometimes it seems to me that a bond between two atoms has become so real, so tangible, so friendly, that I can almost see it. And then I awake with a shock that it is not a real thing. It is a construct that we have to understand things. And then Mulliken says, in a very typical Mulliken sentence, that I believe the chemical bond is not so simple as some people seem to think. Let me trace first a little bit of history about the chemical bond. And in this history, yeah, I can use that. In this history, you see, first of all, the idea of an element from Robert Boyle. You see Dalton's idea of the atom. Interesting, you don't see Lavoisier in here. Then the idea of a molecule in the beginning of the 19th century. And then in the middle of the 19th century, there is an explosion, mainly in England and in Germany, of ideas about the chemical bond. You get the first lines drawn in chemical formulas. You get Butlerov's idea, so now that isn't from Russia, of chemical structures, and Kekulé's structural formulas. And then at 1874, we have the idea of a tetrahedral carbon atom and chemistry in space. Then during the time of the First World War, an independent idea by Lewis and Kossel of the bond as a shared electron pair. And then eventually, at the same time actually, you have during the First World War, the development of chemical crystallography. This is when for the first time, we have the metrics of a chemical bond in terms of bond length for graphite and diamond. And then the quantum mechanics comes in the 20th century. This is a very brief sketch, and if you want to read more, there are some books in English about this. Mary Jo Nye is very good, but especially good about this period in the middle of the 19th century, when in a period of about 20 years, people get a good idea of the chemical bond without knowing how long it is, without knowing its strength, but the chemical structures that we have today go back to that idea. I want to show you that period in the middle of the 19th century. So what is happening there is that people have the idea that atoms are somehow attached to other atoms, and that they can do replacement reactions where one atom can be replaced by another one, a hydrogen by a chlorine, by a methyl group, by a phenyl group. And they are desperate to represent this in some way, but they have no knowledge at the microscopic level. And if you ask them what is happening at the microscopic level, they will plead agnosticism. That is, that they do not know what happens. But yet they have to represent it somehow to communicate with each other. And so here you see some of the representations, and I'll explain them. The first thing to know is that the chemical symbols, C for carbon, H for hydrogen, O, those are there from 1830 on, due to Berzelius and to his authority in the chemical community. But even the idea that a number, a stoichiometric number, so they have weight relationships, but they don't have them right until 1860, because chemists, like physicists to this day, assume that everything in the world is simple. And so that the chemists in the beginning could not imagine that water could be H2O, but they thought that water must be HO, 1 to 1. So even though they knew that by mass, by weight, in water, there was 89% of oxygen by mass and 11% of hydrogen, they could not know that it was H2O. And so they wrote eventually they settled, but they had the formulas wrong in the beginning. But what is important is even though the symbols were established for the elements, there was no rule that this number of the stoichiometric number was written as a subscript or as a superscript. So you see here superscripts here you see subscripts, here you see superscripts. They wrote them wherever they wanted to write them at that moment. But they wrote the formulas in this way, and you see the multitude of symbols that they used to represent that something is connected to something else. Big parentheses, small parentheses, just putting next to each other. Here are Kekulé's so-called Wurst formula, sausage formulas, and this is Kekulé's representation here of a methyl chloride. So you see a carbon here drawn as 4 steel balls. He actually built these physically, connected to each other. And these 4 steel balls here do not stand for anything having to do with the weight of the carbon atom. They stand for the fact that carbon can form 4 bonds, that it has a valence of 4. And so this is a carbon here connected to 3 hydrogens and to 1 chlorine. And you have to know that the hydrogen is not connected to the chlorine. But this was his way of representing CH3Cl. Here is a formula perfectly okay for acetic acid. Here is 1 carbon on the upper left. That is, the pointer is dying out here. there is a carbon that's connected to 3 hydrogens, then connected by a single bond to another carbon that's connected by 2 of its valences to an oxygen, that's connected to another valence to another oxygen, and then to a hydrogen. It's a perfectly good formula for acetic acid, but it's not recognizable today. Here are some of the first physical models by August Wilhelm von Hoffman when he returns from England to Germany in 1865. He makes physical models of simple organic molecules, methane, methanol, and he makes them out of little balls physically connected to other balls, but he makes them square planar at each carbon. There was no knowledge yet in 1865 that it should be tetrahedral. So he makes them and just makes a connection. Okay, so this is a picture at the middle of the 19th century. Here is, for instance, from a museum in Gießen. This is one of Kekulé's first models of the benzene molecule in terms of these sausage formulas. You have to get used to this. This is a carbon with 4 steel balls on the left, and it's connected by a double bond, which you see here, to another carbon. It's also connected to a hydrogen. Then this is another carbon, which is connected to a hydrogen, connected by a single bond to another carbon, which is connected by a double bond to another carbon. It's one of the Kekulé formulas. Kekulé, in a period of 5 years, between 1860 and 1865, puts into the literature 4 different representations of benzene. And this is one of them that did not survive, but it's still there. So what do we have? What we have in the middle of the 19th century is what are called type formulas. The type formulas, the type here does not mean the kind in that sense. It means that it was replaceable. So you had, for instance, toluene here, phenyl, methyl, and the phenyl group and the methyl group were a type. They were replaceable. And here they are, and the methyl group is replaced by an OH. And it is only a few years later that people begin to draw a line between the O and the H in the phenol, because they discovered reactions in which they could replace the H in phenol without replacing the whole OH group, which is what they got first. So that there is an evolution of these formulas, sometimes written with superscripts and subscripts, as you can see over here. So what you have is these, first you have 19th century type formulas of this kind. Then around Kekulé's time, he finally begins to draw structures that begin to look like what we see today. And then comes quantum mechanics, but in a kind of proto-quantum mechanics. Lewis replaces the lines here, or identifies the lines with an electron pair in his theory of octets. And then just a few years later, 10, 15 years later, Linus Pauling comes and gives us the idea of a covalent bond described quantum chemically and describes by a wave function or a valence bond what Lewis described as an electron pair, and what Lewis described as an electron pair was what people had as lines before. So what is happening here? What is happening here is something which is very interesting, but which happens in science all the time. That is, first of all, you have people who are desperate to represent something. They have to represent it somehow, but they don't know how to do it. So they invent a nomenclature. Representation. Representation can be either symbolic or iconic. So iconic means a no smoking sign. You see a cigarette, it's something approximates the real thing. The signs for bathrooms are also iconic. This sign over here on the right side means something to a European, but it means absolutely nothing to an American. That is, but yet it may make a difference between $100 paid in a fine or not. It does not represent that you cannot park an automobile there, but it is a sign that is symbolic. Chemists are very used to this. For instance, the stoichiometric numbers, like in C6H5, are iconic, actually, because they represent a mass relationship. But I hope you do not think that carbon atoms have a C painted on them, on the nuclei. They are not. That's a symbolic representation. We are very used to the description, to the two descriptions. What happens next is these lines are introduced for the sole purpose of communicating to somebody else that one atom is connected to another atom. You don't know how strong, you don't know how far, but it's somehow connected. So you draw a line. And then happens something which the philosophers call reification. This is a fancy word. It exists there in Latin languages as well as in English. It's a word essentially which means becoming real. And it is what my friend, the poet Emily Grossholtz, calls that it's becoming the furniture of the mind. That is, you have an idea in your head, and you know it is an idea, you know it is not real, but you cannot stop it from becoming real in your head. So in that context, the line became a connection which was a line. Then it was reinterpreted in different ways, which we'll see. And then what happens in this transition from the type formulas to Lewis to Pauling is that you have, no one says, we will have a revolution, and from this day on, a bond will be this, which you did not know what it was before. You had the idea of a connection, which went into a line, which went into an electron pair, which went into a quantum mechanical wave function. All along the way, there is appropriation, co-option, parallel and ambiguous terminologies. It's never for bad purposes. It's not meant to fool people. It comes out of the desperation of people to communicate with each other. And so you get this very human and mostly productive turning of one nomenclature into another one. For those of you who know some philosophy of science, this is not Kuhn's idea of scientific revolutions. It is much more like the work of Feyerabend, or maybe Peter Gallison, who is a modern philosopher of science, who has the idea of what are called creoles, or pidgin languages. That is, when two people who don't have the same language, when they need to communicate with each other, when they need to trade, to talk to each other, does one learn the other language? No, they invent a language in the middle that uses some terms from one language and some terms from another language, and they communicate perfectly well to each other with no problem at all. Okay, so what do we have today? What we have today is that a bond is a reasonably persistent connection between atoms. And that seems about as vague a definition as you can imagine. But by the end of these 2 hours, I'll show you that it is a very rich definition. And it has many aspects. But let's talk about what we have. We have, in the first hour, we will discuss experimental ways of measuring bonding. First and foremost, distances from various kinds of diffraction and spectroscopies. We will talk about dissociation energies of bonds. We'll talk about force constants. We'll talk a little about bonding electron densities, not too much about magnetism, and I will do very badly on magnetic resonance parameters, a little bit on spectroscopic material, and at the end something about supposedly direct visualization from scanning tunneling microscopy. Now, there is one sense in which we cannot go back. We have learned that there is, for bonds of various kinds, there is in general a potential energy curve of some sort, which has a minimum. It has a dissociation to something. And we also cannot leave quantum mechanics. So in that potential energy well, if it is deep enough, and some of them are very shallow, if it's deep enough, there will be vibrations of the molecule in that potential energy surface. And what we have learned is that there is a difference between the dissociation energy from the 0th vibrational level. Why is there a 0th vibrational level? Because of quantum mechanics and the uncertainty principle. There is a dissociation energy, this energy over here. There is an equilibrium distance. What you measure depends also on the temperature and how much population you have of the various vibrational levels. We cannot avoid this. But let's talk first about distances. So here is the situation today, or at least that's how it was when I began. There is an X-ray diffractometer of some sort. There is a scattering of X-rays. We have this now. The X-ray picture we have for 130 years. The first determination of a structure from these X-ray diffraction spots we have with us for just about 100 years, a little bit more. And from that, there is generated a map, a Fourier transform, a map of the electron density, and out comes the structure of a molecule, as we usually see it. And what molecule it is doesn't matter over here. Now let's get an idea for the scope of the enterprise. Chemists, in 200 years of frenetic activity, have added to this world about 100 million compounds, reasonably well characterized. Some well, some not so well at all. There is an infinity of them, a near infinity, of course. Your DNA is not my DNA. It's another molecule. But let's put that aside. We're talking about molecules that have been obtained in a laboratory. About 100 million, give or take a few million. Out of those compounds, in the last 100 years, about 1% have had their crystal structure determined. About 900,000 crystal structures are out there. They have been collected in the last 50 years in several depositories. In the beginning, there was one for organic structures, which is called the Cambridge Structural Database, over here. for the inorganic structures, there is another one. There is actually two inorganic ones which are common. The Cambridge structural base has by far the biggest number of structures, about 700,000 or so structures in it. When you do 700,000 structures, you can be sure that some of those structures will be lousy. They'll be done by people not doing science well, and it will be done by equipment that is not functioning well. It doesn't matter. When you have 3 structures, it matters that it's done well. When you have 700,000 structures, the large numbers ensure that there will be that you can get things on average about right. Let me give you an example. Supposing tomorrow you want to know what is the length of a carbon-carbon single bond. Crazy. You would know what it is. But supposing you want to know what I mean by a single bond today would be between a carbon that is connected to 4 other carbons, let's say, and 2 such carbons. So you could, what is the last thing in the world that you want to do for that is to ask a theoretician, okay? What you need to do is to go into the Cambridge Structural Database and ask it, what is the distance between 2 carbons, each of which is connected to 3 other carbons, let us say, other than the one that you're asking about. So what happens? If you go to the Cambridge Structural Database and you ask that, the database answers, "You're crazy, boy. Your question makes no sense because I have 100 million such structures in me." So, okay, so you ask it, "Okay, database, give me your first 10,000 that you find at random." So here's what you get. Actually, J. Siegel did this of the Cambridge Structural Database, and what you get is a distribution around 1.53 angstroms. And actually, that distribution is interesting. You notice it's slightly asymmetrical, that there's a little more on the long side than on the short side, so that it's easier. So that has to do with that curve that we saw, the dissociation curve. Translated into English, it means it's slightly easier to stretch a bond than to squeeze it. I'm translating this into simple English, because that's what it means. You notice the numbers here, 10,000 I added, so this integral is 10,000 structures, but 1,400 are pretty much over here. Some of those are off because, as I said, some of the structures are poor for reasons of either people or equipment. But on average, it doesn't matter. You get your answer pretty well. Now, what you get for most compounds, if you plot the distance, here is a bond which you normally wouldn't ask about, strontium-oxygen. Not many people in this world are interested in strontium-oxygen bonds. But this is what you get from the Cambridge database. There are about 2,000 such structures in the database, and there is one distance which is dominant, and this is very typical for most bonding. Pick any combination of the elements. You will get something that looks roughly like this. There is something around a bond, and of course that's not a covalent bond, strontium to oxygen. It is a dative bond, but the database doesn't care about covalent, coordinate, covalent, dative, or anything. It just cares about the distance. So it is here, and sort of distance around 2.8 angstrom, which is what? which is about the sum of the ionic radii of O2 minus and strontium plus. So strontium 2 plus. So, and then there are this stuff here. I'll talk about this peak in a moment. But this thing here is, what is that? That is long distances which no one in their sane mind would call a bond. It is what happens when there is a strontium here sitting connected to something it's bonded to, oxygen, and then from that oxygen is a carbon and another carbon, and somewhere off in right field is another oxygen. And so it finds that, and the number of such other oxygens around is proportional to the volume of the spherical shell. It's random when it's far away. It's not bonded. It's a long distance. And it grows according to a certain power law as you go up with the further away from the nucleus. This is fairly typical and easy, but many things come out that are not like this. Here is, for instance, iodine from the Cambridge Structural Database. And you see that there is no gap in the middle here. There is a lot of things which are where, for the strontium and oxygen, there was a hole. There were no compounds with that distance. But for iodine there are. There's also more complicated things. One of the amusing things is that the iodine molecule by itself, I2, is not in the Cambridge Structural Database. Why is it not in the structural database? Here's its structure. The reason is that the world around 1950 was run by organic chemists. And organic chemists constructed a database for organic molecules. They didn't care about inorganic ones in the least, even though that year marks the beginning of organometallic chemistry of the transition metals. They couldn't care less. So they defined that in order to be entered into the Cambridge Structural Database, you had to have a carbon and a hydrogen. And iodine doesn't have a carbon hydrogen, so it couldn't get into the database. So how are these other molecules in the database, the ones over here? That's because somewhere else in the molecule, other than the two iodines in question, there is some carbon or hydrogen. So they are in there by accident, almost. So what are these peaks? The iodine-iodine distance, I showed you this. This is incidentally, you see here the iodine-iodine distance of 2.66. Incidentally, you see here two other non-bonded distances marked, 3.27 for 3.50 and 4.27. You should also not ask a theoretician, what is a van der Waals distance? You look at the structure, let's see, how can I say it? The structure solves Schrödinger's equation exactly without approximations. You don't have to worry about which functional to use. The structure uses whatever it has. So look at the structure to tell you what a van der Waals distance is, and it tells you right away there is no single van der Waals distance. There is 3.50, 4.27. That gives you an order of magnitude estimate. I will come back to this again and again. It is only the simplicity of our minds that insists that there is a single answer to any question. It is the same simplicity of mind. Like the question is, what is a van der Waals distance? It is the same simplicity of mind that is in the mind of an President of the United States when he says, if you want to solve the drug problem and the immigration problem, you build a wall between our country and Mexico. That is so crazy. But what I want to show you is that scientists are no better. They always want, tell me that there is a bond. Tell me that there is no bond there. And the answer may be it's in between. Maybe there is a bond. Maybe there is a partial bond. It's okay to do that. Okay. So what are these things over here? Here is, for instance, a large peak. The large peak over here at 2.95 angstrom. It comes from triiodide ion. There are hundreds of structures of triiodides. And there is electron-rich 3-center bonding, but that's the way we choose to describe it. It's centered around 2.9 angstrom. You can even do what's called a Bürgi-Dunitz plot, where you plot one distance in triiodide versus the other one, and those thousands of structures are taken apart into a beautiful hyperbola, which translated into English says, if you make one bond shorter, the other bond gets longer. This is the triiodide, centered around the symmetrical one at 2.90. Here is the iodine distance in iodine itself. That electron-rich 3-center bond is weaker than the iodine-iodine single bond. How do these get into the Cambridge database? These are all from the Cambridge database. They get in because there's a counterion. And the counterion is an organic ammonium ion, typically, or something like that. And it's got a carbon and a hydrogen. So it gets in. Not because of the essential part, but because of the non-essential part of the counterion. It's amusing. Okay, this is one of the most important papers of the last 10 years. This is Santiago Alvarez's paper about a cartography of the van der Waals territories. Santiago loves the Cambridge Structural Database even more than I do. And so he has done, this is a single person paper. What he has done, he has picked one element, oxygen, and he has, with great labor, gone through the Cambridge Structural Database and looked for all the structures which contain distances to oxygen from 90 or other elements, okay? 2 of them are strontium and rhodium here, but in his paper you will see 90 others. And he plots out a map. And for some of them, I showed you strontium oxygen. This is the simplest kind. There is one distance, then there is nothing here. Iodine was more complicated. There were things in here. And then they go up. But in every one of them, he sees a little peak or a big peak like that. A peak at not a single bond, coordinate covalent bond, not the random distribution, but some more structures favored in some intermediate region, which is typically 1 to 2 angstroms longer than a single bond distance. This is a typical situation here. These are the van der Waals distances. I can see no better physical demonstration that a van der Waals bond exists than seeing it come out from these crystal structures. It is a very direct evidence for a van der Waals attraction. Okay, I could go on talking about crystal structures for a long time, because I received my education in a group of crystallographers with William Lipscomb, even though I did not do crystallography. But I don't have time. I just want to show you one more structure. We used to think that because of the physics of X-ray scattering, that you could not locate hydrogens well by X-ray crystallography, and that you had to do neutron diffraction in order to get distances to hydrogen well. It turns out that today it's possible, as this paper shows, which was in Science Advances just 2 years ago, it shows that you can, with proper investigation, get even hydrogen locations from X-ray crystallography. I have to leave X-ray crystallography. I have to leave distances because I have to get to the other things. So let's talk about bond energies. So that is one other criterion of the strength of the bond, is the depth of that well that you saw in the potential. How deep is that well? How strong is the bond? So the well by itself tells you that if you heat up the molecule, it'll break apart. Okay, that you can use that direct method, the thermal decomposition of a bond, to get a bond strength, a bond energy, but you have a problem. The problem is that it's usually, by simple heating, it is the weakest bond in a molecule that breaks. So what if you want the strength of a bond that is not the weakest bond? You got a problem then. But actually, it's not so bad. And today, most bond strengths, when they are estimated spectroscopically by a Bornhaber sequence, which goes typically like this. So this is a paper where you can read about this. So if you want, for instance, if you heat ethane, it will break apart by breaking the CC bond. But supposing you want the CH bond strength. So what you do is you do one experiment where you shine light on the ethane molecule and you measure the threshold energy of the light that is necessary to break off a hydrogen. Turns out that while thermally a CC bond breaks, photochemically a CH bond breaks. So that's good. You have a handle then. It actually goes off as H in an electron, but you can measure this energy to a hundredth of an eV with ease. And then you take this ion and you have it running down a mass spectrometer, and you can measure the energy of attachment of an electron to the cation while it's going down a mass spectrometer. And actually what you are measuring is the ionization energy of the ethyl radical. This is the ethyl radical, ethyl cation. It's the inverse of that. And then by just adding these two, you don't have to believe me, we do believe in thermodynamics. We do believe in thermodynamics. That is why we teach our students the Bornhaber cycle so well. If you add these two up, the ethyl cation cancels out, the electron cancels out, and you have, this is what you want from these two measurements. And these can be done usually to very high precision. So we have some of these numbers. Some of them are startling and surprising. Some are not. It does not surprise an organic chemist that to break ethane to two methyl radicals takes less energy than to break ethylene into two CH2, two carbines, and let's say they are in a ground state. But sometimes the results are surprising. I know this is hard to believe, but to take silane into Si2H6, introduce silyl radicals, cost a certain energy, to take the disilane, which many people know is not a very stable molecule, and to break it into 2 carbene, actually costs less energy than it takes to cross the single bond. This is not a theoretical artifact, it's an experimental measurement. So it's really true. And why is this so? That's another story. It has to do with the weakness of the bonding in here and the special stability of the products of the carbenes. Let's talk about the vibrations. So distance, energy, now the vibrational force constant. So what this has to do with is with the fact that near the bottom of the well of any molecular potential, it is approximately quadratic for the vast, vast majority of molecules. And this was recognized early on. And so people classically thought of this, that the 2 atoms connected by the line were connected by a spring with a force constant, K, so that the potential energy here is represented by 1/2 kx squared over here, and that force constant is a 3rd measure of the strength of a bond. It could be used as an indication. So here is a typical vibrational spectrum. It happens to be 2-propanol, and there are some sharp peaks. This is low resolution. This is the way an organic chemist would see it. It's diagnostic on some things, but not diagnostic on others. Typical spectrum. Now, not very fashionable today, but done routinely about 30, 40 years ago, were so-called vibrational analyses. So vibrational analyses where you observe the spectrum of a molecule. Here is the spectrum. You see many vibrational lines. Some of them are the normal vibrations of the molecule. Some are overtones or harmonics. It is no different than when listening to as I did last night, to a flamenco guitar being played. When you hear a guitar being played, what you are hearing is the direct tone, but you are also hearing the harmonics and the overtones and combination tones, which give the characteristic timbre of the instrument. So this is also has some characteristics. So what you do when you have a molecule, this molecule happens to be a nice organometallic molecule. This is trimethylene methane, C with 3 CH2s, and it's connected to iron tricarbonyl. It was made in the early 70s, and immediately when it was made, people did a vibrational analysis because it was a highly symmetrical molecule. So what they do in a vibrational analysis is they assume there are springs between force constants between the one of the groups assumed that there were springs to each of the carbons outside and also to the C and between the C and the O, and then they had a computer calculate the frequencies due to their assumption of the springs, and then they compared the frequencies with experiment. And from that they got the spring constants, the K's in the 1/2 kx squared. And one group did it, and then another group did it, and that group made some different assumptions about the springs. Instead of having springs all to the 3 carbons, they had one spring to the molecule as a whole, and not to the 3 carbons. And the two published, as you see in good journals, vibrational analysis within 1 year of the same molecule. Now, this is a very interesting situation in science. People are doing what they think are the same thing for the same molecule, okay? Such a situation in science is not good for the second group who does it, okay? But it's the best thing in the world that can happen for the community of science. And it's too bad that these things don't get published. The reason is the following, that it's only when two people, two groups in the world do what they think is the same thing, that we get a real estimate of the errors in the measurement. Because each one thinks they've done the best thing. And there are systematic errors, there are statistical errors. They only give you the statistical errors. They don't know they have systematic errors. But because they have done it on different instruments in different laboratories, you get an idea of what the errors are. So in this case, here is the work of the two groups. And what these numbers that you see in this table are, they are the Ks, the force constants in the vibrational analysis, and they agree pretty well, though they're off by 3% for the strong bonds, like a carbon-oxygen. But for some of the bonds, they're off by much more, and sometimes there is even a change in sign in some of the things. So here is what the second group said. It turned out that the second group who did this, an extremist who was known in the community, Miller, who was significant other force constants. Two different valence force fields are now available for trimethylene methane. That was the other group. And both reproduced the starting frequencies well. But the individual force constants differ considerably. Which one is right? Which one is right? And he says, we believe that most force constants which have been derived from large symmetry blocks should be regarded with skepticism. There are several sources of uncertainty. The different sets will reproduce the frequencies equally well. It's then almost impossible to tell which is right. So basically what is here is that the ratio of observations to the number of assumptions is rather low. So it's very hard. There are things in the literature today which are based on a ratio of observations to assumptions, which is less than 1. And you really don't know if things are right at all. But this is a very honest person telling you how it is. Now, what I've just talked about is 3 measures of the bond strength: the length, this distance, the depth of the well, and the force constant. And usually there is a correlation. And the correlation is the obvious one. The deeper the well, the shorter the bond, the larger the force constant. This has a name. It's called Badger's rule. And it's usually valid, but it sometimes is not. You can see here that here is a bond. This happens to be the C2 molecule, a very simple diatomic. And you see here that there is a bond, which is here, but here is a well that is obviously more shallow, has a smaller bond energy, but is shorter. That's interesting. How can that be? It's interesting. So it's interesting to find out. There are bonds that are, there are all kinds of things, and there is an article here. Okay, let's skip that. Let's talk about electron densities. Today, it is possible with good measurements from X-ray diffraction done at several temperatures, including low temperatures, and a combination with neutron diffraction. It is possible in ideal cases, and Phil Coppens was a master of this. He's no longer alive. It is possible to get from X-ray and neutron diffraction experiments directly the electron density in the molecule. And those are the red lines here. Please ignore the black and the blue for a moment. But the red lines are contours of the electron density. And you see here that there is a lot of density around the oxygen, around the carbon. This happens to be methyl carbamate here that is being plotted. So you can get the electron density. And there came a dream, a light in the eyes of the experimentalists and the theoreticians. That is, when we can get the electron density in the molecule experimentally, that what we can do is subtract the electron density of the atoms that are in the molecule and get the difference in density between the atom and the molecule, the sum of the atoms and the molecule, and that'll give us the electron density in a bond. It was a dream. It's not very good. Here is first about the electron density in a bond. Here is BF3, and there's a little map of the electron density in a molecule. And what you see here is the BF3 is a planar triangular molecule. You see here big hills at B and F. What is that density? That's not the bond. That's the 1s orbitals on the boron and the fluorine. And so they are the maximum of the electron density. And along, everybody knows that there is a bond between boron and fluorine in BF3. But actually, and this will come in the theoretical part, actually, the electron density at the midpoint of the bond is actually a minimum in the total density along the line joining the two atoms in a bond. It's not a maximum. It's a minimum, but it's a maximum with respect to two other directions going off. We'll come back to that theoretical part. So here is what people did when they took the electron density in the H2 molecule and subtracted from it the electron density of two hydrogen atoms. And what they got was, so this is a plus means more electron density, dashed lines means less electron density, and so what they got is more electron density in the region between the nuclei that looked like the bonding density until they did it for fluorine, F2. And when they took F2 and took the experimental and theoretical electron density in F2 and subtracted from it two fluorine atoms, spherical, they got that there was no density in the middle of the bond at all. Now, it's true that the fluorine-fluorine bond in F2 is a weak bond. It's only 35 kilocalories, but it's still a bond. But they got no electron density there, according to this. So what was wrong was, what went wrong? Eugen Schwarz has analyzed this in detail. What went wrong was what you subtracted. You should not subtract spherical densities. You should subtract, because a fluorine atom by itself does have a spherical density. But a fluorine atom prepared for bonding in the F2 molecule does not have a spherical density. It has less electrons. The one electron that's doing the bond is in a p orbital. The others are lone pairs that are filled. And once you subtract the fluorine atom prepared for bonding, you do get a bonding density. But then you're in a trouble, because what you have to do is each time know what to subtract, which is just as bad as what you did initially. So that doesn't get you anywhere. We haven't talked about, I've just gotten through half of the list, but I don't have time for much of it. But let's talk a little about magnetic criteria for bonding. The usual situation, the magnetic and spectroscopic criteria for bonding happen, you apply these mostly when there is weak bonding. Here is the situation. Here is how it applies. If you have a bonding orbital called A and an anti-bonding orbital B, and if they are not far apart from each other in energy, if they're far apart in energy, you've got no trouble. You've got a bond. But if they're close to each other in energy, then you have 6 different ways to put the electrons into the 2 orbitals, 1 triplet and 3 singlets. Oh, what's a typical molecule that does this? Here it's the copper acetate dimer, a classical case of a question of bonding. What happens, I don't have time to go through this, but if you go through the inorganic chemistry, you'll find this is copper 2, and you have 1 electron in an x squared minus y squared orbital, and the question is there a bond between the coppers? The distance doesn't help you. It's a distance of a bond. But there is a singlet and a triplet, and the general thing is, this is the balance between high spin and low spin. Low spin is the situation of having a bond. It's what happens when these 2 levels are split apart. So when the 2 levels are close to each other, that triplet has a chance of being the ground state of the molecule. When the 2 levels are far apart, you have the situation of a typical saturated organic molecule. The triplet has no chance for being the ground state of the molecule. The ground state is a singlet. So it's this maybe mixed with a little of that configuration. And so this has been used as a magnetic criterion. Spectroscopic criteria are very similar. Here the focus is, again, 2 levels which can be close to each other or far away from each other. Far away from each other means bonding. Close to each other means less bonding. So what you look here is at a blue shift of an electronic transition as a measure of bonding. The last thing I want to tell you about is something that's of the last 30 years, the last thing about experimental measures. Not a word of theory so far, is scanning tunneling microscopy. So from the beginning, this was promising. This promised, so this was done at IBM. This was done initially, and so it was accompanied by company hype. And the advertisements showing proudly that an IBM scientist had done this, and it was a great achievement, typically said the following: now, after waiting for 2,000 years after Democritus, now finally you can see atoms through scanning tunneling microscopy. What you do in scanning tunneling microscopy, of course, is you have a conducting surface, you have a conducting tip of some sort, you measure a current tunneling across, and you have exquisite control both in X, Y, and in Z in this. Control to within an angstrom of the things. So you can measure the tunneling current, and you can then do it in a mode where you determine with the position of the atoms. So this is the remarkable achievement from the beginning, the so-called silicon 111 reconstruction of that surface. A beautiful example of the power of scanning tunneling microscopy, which in fact showed you silicon atoms on the surface, and an unusual reconstruction. So when I heard this, that now after 2,000 years you can see atoms, I went through the ceiling. My myself, because what a travesty to 200 years of chemistry. Not even counting X-ray diffraction, but from 200 years of hard work, and in the last 100 years with X-ray diffraction, we knew the structure of molecules in atomic detail without waiting for any microscopes. That is the great achievement of chemistry, that we knew these things indisputably, incontrovertibly, without waiting for microscopes. The same is true for biology, for DNA. There were no microscopes around to show us. It's through the hard work of smart human beings and our fallible senses and the extension of our senses that our instruments represent that we learned that knowledge. And it was confirmed by these pictures. But we didn't wait for those pictures. So what can you see? Today, now we are 40 years past the discovery, almost 40 years, 30 years past the discovery of, and what we can see today is something like a phthalocyanine molecule, and it looks like this, approximately. We are by and large a long distance away from atomic resolution on a regular basis. Actually, we can see something much more interesting. Because what we are observing in the STM experiments is a tunneling current between one tip and another tip through a molecule that is on the surface. What we are observing is, and we can bias the tips so that either the electrons come from a lower filled orbital or from even an unfilled orbital of the molecule. What we can measure in STM, that's what we measure over here at lower right, is for a pentacene molecule, is we don't measure the position of the atoms, but what we measure is the electron density in a molecular orbital. Not the wave function, but the wave function squared. So this is very interesting. This gives us a picture of a molecular orbital directly, and that's why the theoreticians are so interested. So here is what you see in the last 2 years. What you see is atomic force microscopy, modification of this. The actual observation produces something like this, which is like that molecular orbital. But then there is a massaging of the data, and what you get is a picture of the pentacene molecule. This was worth 2 papers in Nature, this picture over here, which shows you the picture of pentacene molecule, and now you are below 1 angstrom resolution. You are at about a resolution of about 0.2 of an angstrom or so. So this is Nature 2015 for pentacene. This is Trotter in 1946 with an X-ray diffraction experiment, which gives you more information about the molecule. So maybe they'll get there in the scanning microscopy, but they're not there yet. X-ray diffraction gives us the metric information about molecules superior. This is very interesting. Why is it more shiny at the ends? I don't know. But I've gone through now at great effort some of the, not doing justice. You notice I said nothing about NMR coupling constants, for instance. Nothing. But I've gone through, as honestly as I can, the various experimental measures of bonding that we have. And now we're going to stop for 10 minutes, and then we will continue with the theoretical one. Thank you.
No, it's okay, Rod. Déjame probarlo yo también. ¿Dónde están los...? Yo he echado un cable, es que me ha dejado, está con mi cable. Yo he echado un cable con todo esto, porque hay que tener sobre el sensor de metal. Sí. Se debería encargarse el comando de la... Sí. Es que muchas veces, por ayudar, se... Voy a verlo, ¿vale? La gente me lo que ayuda un poco y cuando falla algo, es de aquí de la sala que el técnico te debería... En lo que te puede ayudar me avisa. No. Puedes ir. Sí, yo voy a estar aquí. ser las pilas, dices tú?
No, lo suyo sería esto. ¿No ves? Un segundo. ¿Funciona? Estupendamente.
Pero ahorita cuando empezamos por arriba...
¿Esto dónde engancha? ¿Aquí?
Vamos a buscar otro. Está...
Solo... ¿Este botón? Yo creo que ese botón está mal. Bueno. Hola. Es que funciona estupendamente, tío. Es que funciona. Espérate.
go. We'll use this. This one. Yes, of course, yeah. Okay, so here is a detail of a portrait of a painting in the Vatican by Raphael. And it portrays a school of the school of philosophers. So this refers to the classical Greek and Roman philosophers. At the center of it are Plato and Aristotle. Okay, so even in the time that he painted, and for the audience he painted of educated priests, he sometimes could not be sure, the painter, that the audience knew who was Plato and who was Aristotle. So in order to do that, he has each of them carrying a volume, and this is Ethics, and this is Timaeus, it says on it. So that helps you to identify who is Plato and who is Aristotle. But the reason I show it to you is Aristotle, despite centuries of malignment for leading physics astray, was a very careful observer of nature. There is a book by him, Animalia, which describes animals in the Mediterranean in great detail, so you could identify them today. But Aristotle was of this earth. That's why he's pointing here, the gestures. And Plato, on his right, he's pointing up there. So Plato was a believer in ideal forms, and that the reality was just a reflection of the ideal forms that exist up there. So Aristotle is experiment, this is theory here. Okay. So let's talk a little about theoretical measures of bonding. And some of this will get quite technical, but I hope to keep it understandable. But first I want to show you something, a remarkable document I found. I didn't find it, somebody else found it. So you know that Niels Bohr in 1913 wrote a remarkable paper based on the old quantum mechanics, where he quantized the motion of the electron in the hydrogen atom and was able to obtain the Rydberg formula, the Bohr formulas. At the same time, Bohr, that he published this paper in 1913, he was on a postdoc with Thomson, unsuccessful. He wanted to go to Rutherford, and he wrote to Rutherford telling him about his work, just like you would write today to somebody, no different. This is 104 years ago, 105 years ago. And he writes to Rutherford and he tells him that aside from the new theory of the atom that he, Bohr, has, that he also has a theory of molecules. Now, he had a brother who was a medical person. He had other relatives. He knew some chemistry. So here from his letter in his handwriting is, and this was published more recently, is Bohr's construction of the electron motions in the molecule. And if you know the Bohr atom, what he did was he had the electron move in a circular orbit, and he quantized the angular momentum of the electron to get the Bohr formula. So he's going to do something like that for an H2 molecule. He's going to take the two electrons in the H2 molecule. He's going to put them into a circular orbit on opposite sides of the orbit. He knew about electron correlation, that the electrons will stay out of each other's way on opposite sides of the orbit. But he's going to vary the radius of the circle and he's going to adjust that in order to get the strength of the H2 bond. He did this also for water. He knew from somewhere else that water was not linear. He did it for O2. Here he does it for ozone. This is a remarkable picture because he realizes that for ozone there are two valence structures, one which has 3 electrons bonded here, another one 3 electrons bonded here. He did not know that ozone was bent. That was not known yet. And here he has 2 electrons in this bond and 4 electrons here. Let me translate this for you. This is a resonance structure for ozone with a single bond between the 2 oxygens here and a double bond on this side. He knows about resonance structures in 1913. Here is for methane. He knows methane is tetrahedral. Here is acetylene. And this was never published. Remarkable early excursion into chemistry from Niels Bohr about bonding. Okay, so where are we? Again, we cannot go back some things, so we have some basic ideas about bonding and antibonding. So if you have 2 orbitals, and they are on 2 separate centers with wave functions chi1 and chi2, that they interact, the orbitals seem to repel each other in energy. Lower one goes down and mixes into itself the upper one in a bonding way, and the upper one goes up and mixes into itself the one below it so as to take a node. So the general picture here is universal, and it is always true that there are less nodes in the bonding orbitals than there are in the antibonding orbitals. Where does this come from? This is not something, it's actually not quantum mechanics even. It's again that guitar string that I heard. If the guitar string has a node in it, it's at a higher frequency, higher energy than the guitar string that has no nodes in it. So this is true of classical systems as well. It's true of a particle in a box. If any of you have done the simplest quantum mechanical problem of a particle moving in a box with no potential, but with infinite walls, the lowest wave function has no nodes, the next wave function has 1 node. That's what you're seeing over here. This picture is actually quite rich, so let me explain some of the things in it. What it says is orbital interaction. Notice there are no electrons in here yet. We have not put in 0, 1, 2, 3, or 4 electrons, though we know 4 is the maximum for this system. We have not put them in yet, but in terms of the orbitals interacting, 2 orbitals will mix each other. The lower one will be stabilized by the mixing, the upper one destabilized. And mixing and interaction are synonymous. They are different words in English to describe this. But also, what is not perhaps seen, what I want to remind you of, is that mixing and interaction also implies electron transfer. So let's talk a little about that. So here there were initially 2 electrons. Let's say there are 2 electrons here and no electrons in chi2. Let's say they're that way. Then afterwards you have the wave function. This has mixed in that. But you know, it only can have 2 electrons in it. You cannot create or do away with electrons. If there are 2 electrons here, there are 2 electrons here. Since they are distributed over 2 centers, there must be less than 2 electrons in the center at left and a little bit of or a lot of an electron in the center at right. so that there has been electron transfer from this, if this is filled, a donor, to this, if it's unfilled, an acceptor. So orbital interaction means orbital mixing, means electron transfer. Those three things are connected to each other. That's the beginning. Now, whether the system is stabilized or not depends on a number of electrons. If you have two electrons, there will always be stabilization. And you know, it doesn't matter that these two are the same energy, even if they are of different energy, like here, you will still get stabilization for two electrons. If there are 4 electrons, both orbitals occupied, then if the splitting is symmetrical, you'll get no stabilization. But it turns out that if you include overlap in the calculation, that the splitting is always unsymmetrical, so that the upper level goes up more than the lower level goes down. And so if you have both filled, you get a net repulsion. You're going to tell me that 2 helium atoms have a van der Waals attraction between them. Indeed, they do. But it is tiny, and that's not chemical bonding. That comes, if you want, from electrostatics at some higher order of a multipole interaction, from an induced dipole to induced dipole interaction, or from a polarizability of both of the fragments. We understand that from 1930 on, but it's not what we usually call chemical bonding. Most of the helium potential energy curve is repulsive. There is a very small minimum due to the van der Waals attraction. Okay, what happens when we go to something more complicated than 2 hydrogen atoms? And here is, again, something that you have seen from high school through university, and that is you have 2, let's say, in a homonuclear diatomic, a 2s and a 2p. Let us say this is the nitrogen molecule. You have the 2 s's interacting to give this sigma G, sigma U combination. You have the 2p is interacting, and you get, and there is some little assumption in here which is important, and that is that the 2p orbitals along a line like this, interacting in a sigma way, that they interact more, which means they are split more. Interacting more is just the splitting over here. It's no different. They are interacting more. Sorry, this is what I had. They are interacting more, the sigma orbitals, than the pi orbitals, to give, again, a bond. So what's going in here is something about the magnitude of the interaction being proportional to the overlap, something about the lower orbital has fewer nodes than the upper orbital, no more than that. Okay. This is what we teach students at the Liceo. Okay? This is when you go to graduate school. So this is in a sense, or in the university. So what we then go on to teach students is, yes, you have seen the beginning of the story, but that's not the whole story. Now, I'm going to put it in technical language. The technical language here, this is quantum mechanics. We cannot escape that. The technical language here is that of perturbation theory. And perturbation theory comes in several orders. And what is happening here, when you split these 2, and when you split these 6 orbitals into 1, 2, 2, and 1, what you are doing is 0th order perturbation theory for degenerate orbitals, orbitals of the same energy. And after you've done that, you are not finished. That is the beginning. And that is what we tell students in high school, because it has a lot in it. And let me tell you another thing we tell students in high school. We tell them, we want to tell the students that in H2 there is a single bond, and in N2 there is a triple bond. So how do we tell that? So I'm telling you what we usually, I don't know if this is what you teach at the Liceo, but I'm guessing that's what we teach at the Liceo, because it's no different for ours. So H2 would just have 2 orbitals in here, 2 electrons in here would have a single bond. So what we tell students is that to get a correspondence to what organic chemists mean by a single bond or a double bond or a triple bond. I remember how that went. 19th century connection, then a line drawn, then Lewis interpreting the line as as electron pair, then Pauling interpreting that as a covalent bond, Mulliken So here, in the same spirit, this 2 electrons in a bonding orbital are interpreted as a bond. Why is that done? In order to make a correspondence to what is normally done for these things by organic chemists, let's say. So how do we get the triple bond in N2? So 2 electrons, so how many valence electrons does N2 have? Each nitrogen has 7 electrons. Only 2 of those are in a s level, so each nitrogen has 5 valence electrons. It has 7 electrons in all. So you have in 2 nitrogen molecules 10 electrons. So you put 10 electrons, 2 here, 2 here, 2 here, and 4 into that. And now you fill an orbital that is bonding, anti-bonding, and so you say this cancels that one. A contribution to a bond order of 1, -1, 1, and +2. +2 because there are 4 bonding electrons. You add those up, you get 3. And everyone is happy in high school. What happens in high school and Liceo is there is a contract between the professor and the students, an unwritten contract, that the world is simple, and I'm going to tell you how simple it is. Okay? Now what happens in graduate school is you learn the world is complex, and you also fall in love, and you learn the world is complex and not simple, yes? Okay, because you fall out of love just as well as you fall into love. So the world is complicated. And what happens when you start from the simple picture is you have prepared for a good analysis, and part of doing the perturbation theory are now lapsing back into technical language, is that there are 2 sigma G orbitals and there are 2 sigma U orbitals. And one of the rules of this world in perturbation theory is, if anything can mix, it will. It's just a question of how much. But it will mix. So these 2, this one over here, 2 sigma G, and this mix in, and the combination that goes down as a result no longer looks like a pure S combination, but has mixed in some P character and looks like that. It becomes more bonding than this. And this combination in here, which was anti-bonding, had a terrible node which hurt it, which cost it an energy, mixes in that one up there and mixes in such a way as to move. If 2 orbitals mix, the lower one goes down. Translated into English or Spanish, it goes down because it's stabilized. So what put it up? What put it up was electron region, electrons in the nodal surface. So it gets the electrons out of where it hurts. That's all it's doing. It's pushing the electrons to the outside because they hurt on the inside. So that's this. And it transforms into what looks like a lone pair combination, which is better than having as an antibonding orbital. And now the same thing happens to the upper member of this pair. Now here comes a terrible, terrible temptation. This is the temptation to say that all children are above average. Okay? If something goes down and becomes more stable, something else goes up and becomes less stable. So that it will be very nice if this orbital here, which is already bonding, would become more bonding, but it cannot because something below it has become more bonding. So the only thing it can do is to do the opposite thing, which is to move the electrons to the outside. This is a little subtle, but that's what this one is transformed. And so now we get a picture, this is graduate school, where things are more mixed up, but it makes more sense. And it actually, I'll tell you how it makes more sense, but it also causes a problem. It makes more sense because this is a bond. This is no longer a bond, but a lone pair combination. This one over here is also a lone pair combination. And so it makes sense because instead of bond, antibond, bond, we now have bond, lone pair, and another a pi bond. It's much more corresponding to, don't turn on the light. It's all right without the light, don't worry. They will see it. It's much more, here is our Lewis structure of this. This picture is actually much more on the right, closer to the Lewis structure, because the picture on the left had no lone pairs. But now you see the lone pairs coming out. Okay, now what is the trouble with the picture on the right, which is the better picture? The picture on the right is that you have lost the organic chemist's point of view that this is a bonding orbital, anti-bonding. Instead you have this is a very bonding orbital. This one is slightly non-bonding, or slightly anti-bonding. That one is slightly bonding. You now have no longer a +1 and a -1 for the bond order. The world is more complicated. Instead of +1, it's +1.2 and -0.2 and something like that. Okay, so that's the situation, roughly. Okay, now Mulliken faced this, and early on decided to invent a measure of the strength of a bond which could carry over to the new picture. And this measure was that if you had an orbital, which was a linear combination of two atomic orbitals, which was, say, individually normalized, that is, the square of the integral of the square of the wave function is 1. If you normalize this integral, this wave function, sum of two linear combinations, and you took this means every orbital should be normalized, so this integral is 1, that is C1 squared, you put it in there, times integrate by 1 squared, C2 times by 2 squared, C1, C2, 2 cross terms, and this is the overlap integral, D1, D2. That is the integral of two wave functions multiplied by each other, integrated over all space. If you take that, you get C1 squared plus C2 squared plus 2C1 is 2. And so what he said, let me assign as a bond index, as a measure of bonding, this term term over here, and he called this an overlap population. And it's 2C1C2S12. And it is a bond index. It behaves like a bond index. So what do you want a bond index to behave like? If the wave function is a bonding one, plus and plus, or minus with minus is just as good as plus with plus, you want this product to be positive. But if the wave function is a plus and a minus on the two centers, then you want this thing to be negative. And that's what it behaves. You notice it has an S12. That's not a bad thing. Let me tell you why. We don't even talk to chemists about it. We sort of assume it. But can you form a bond between a 1s orbital on carbon, a 1s orbital on carbon, and let's say a 2s orbital on the other carbon? Why not? Why not? They might form an in-phase and out-of-phase combination, but the S12 is very small. So you only form bonds between two orbitals that are close to each other in extent in space. So the overlap is not a bad region. Anyway, this is a molecule population analysis that I've described for you. And it's not the only one. So let me just right away show you another crazy overlap population definition, which would give also what we want to be, that it would give a positive number for a bonding orbital and a negative number for another bonding orbital. What if instead of C1, C2, S12, I took C1 raised to the third power and C2 raised to the third power times S12? Perfectly okay. It would give the same thing. But it's crazy. It doesn't, this is the simplest bond index. Now, out there in the literature, you will see different people use different bond indexes. They have names of people, Weiber, Mayer, Levine, all very clever people. What you should conclude from the fact that something which has to do with physical, something which has to do with physical things that has 4 different names attached to it, what you should conclude from it is whatever is being calculated is uniquely defined. You will believe that these are good scientists that have made it, so that they've defined it uniquely, but is totally arbitrary. You see, that's what you conclude from the fact that there are many things that are called by the same name. Not totally arbitrary, but are arbitrary to some degree. Okay, so now I'll come back to the molecular overlap population. I've just showed you, it has taken me some time, but I have talked a little bit about what is a measure, a bond index at least. And there are different bond indices. Let me talk something else. This is the atoms and molecules method or quantum theory of atoms and molecules introduced by Bader, who was originally an organic chemist but converted to be a theorist. He is no longer alive, and he introduced this over a period of years, and it has to do with this electron density, analysis of this electron density. So here is BF3, that nice planar molecule. And what you see at upper left is the electron density in the plane of the BF3 molecule. And you see what I already told you is that the maxima of electron density are on the atoms. They are due mainly to the inner core 1s orbitals. And this is a slice through a plane that runs through a BF bond. So it looks sort of the same, but it's just one BF bond. And what you see is that the electron density is a minimum along the direction of the bond. This is very difficult for chemists to believe because we are so focused on a bond, but it really is so, as this picture shows. But it's a maximum in two perpendicular directions. So this is what Bader called a 3 minus 1 critical point. So here is, so what he plotted was, he showed, go back a little bit, he showed that if you, now it gets a little more, still more technical, if you plot the gradient, gradient is just the derivative with respect to the x or y or z directions, it's a vector. If you plot the trajectories traced out by the gradient vectors, that in this scheme over here, then this is the BF3 in this view, in the plane, this is perpendicular to the plane. The gradient vectors all must terminate at the atom. Turns out that that is so. And then that must mean that there are some surfaces here drawn by a line in a plane along which the gradient is 0. And these define regions in which the electrons can be assigned to a given atom. This to these boron, these to the 3 fluorines, or if you draw along a BF bond, there is the gradients terminate at the boron and the fluorine. There is a line here which passes right through the mid-center of that bond where the derivative with respect to one direction is 0. That is over here. And that's a minimum with respect to that. So he atoms and molecules based on these gradients. And then he defined a bond path as the line between two atoms, which is the line of maximum density linking the nuclei of the two atoms. The line of maximum density, even though it was a it's a line of maximum density along the path between the two atoms, but it's actually a minimum. It turns out whole quantum theory on experimental facts if you do your crystallography well. So here is this Phil Coppin's study of methylcarbamide, this molecule, and the red lines are the density, and the blue lines are the gradients. And these black lines now are the divisions between the atoms. So all the electrons here in that little domain belong to the oxygen. You notice these domains go out to infinity? So in this picture, there are no balls around the hydrogen or fluorine. There are regions that go out to infinity. We tend to think there are balls of some sort. Not in this picture, but they are divided up into atoms. And he felt that you could define a bond by taking the bond path between the boron and the fluorine, and that point, what he called a bond critical point. And what Bader said is you have a bond between two atoms when you have a bond path and you have a bond critical point. So he felt he had a unique way of defining a bond. Okay, somewhat long to get it in here, but you can see a little bit the driving force here. Okay, this got into trouble. Let me show you how it works in some things. So here is, for instance, 2 organic molecules. One is phenanthrene here, and this is biphenyl. And biphenyl not in its favorite conformation, but planar. And so what you see here, you see the little red dots? Pay attention to the red dots here. The red dots are Bader's bond critical points. And they occur at the midpoint of each CC bond. And they occur along a CH bond a little bit along out toward the hydrogen. If you stopped there, you would be very happy, because Bader's picture restores bonds from these bond paths and bond critical points. But then it creates some weird things. For instance, it creates a bond critical point between the two hydrogens over here. And the same over here. And every organic chemist knows there is no bond between those hydrogens. Okay, how do the organic chemists know there is no bond between the hydrogens? So it's a long story. But organic chemists, remember, organic chemists are the people who can make any molecule in the world. Okay? I have infinite faith in the ability of organic chemists to make molecules. So they can make a molecule where this hydrogen is replaced by a bigger group. What do I mean bigger? CH3, well, start with halogen, CH3, tertiary butyl group. They can make these, sometimes with difficulty. What happens is it's harder and harder to make these molecules when you put large groups there. And it's even, when you put methyl groups there, you can see in the X-ray structure a deformation, that the two methyl groups go out of plane a little bit. They really don't like to be next to each other. The same thing happens over here. So that this is what is behind the organic chemists believing that that those positions, and here is the language that you have heard and that organic chemists use, those positions are sterically hindered, which says they are in trouble if you put large groups there. Okay. Now the real sort of problem came to the fore when you looked at helium in C60. Okay, so C60, Buckman's the fullerene, is a very nice molecule. You can put a helium atom inside C60. You do not do this by rational synthesis. You do it by heating the hell out of C60 to 1,000 degrees C in a helium atmosphere. The C60 is jumping around wildly, and sometimes it opens a hole, sometimes the helium atom goes in, it closes up as you cool down. And once the helium is inside C60, you can tell by NMR that it's there in small amounts, because there's a chemical shift for an isotope of helium in there. So you can tell that it's... So you can put a helium atom inside C60. So here is a Bader calculation on helium in C60. If you focus first on the 6-membered rings and the 5-membered rings around the periphery, you see everything's okay. There is a bond critical point at the center of the bond. But going out from the helium atom in the middle to every one of the 60 carbon atoms of this molecule, there is a bond critical point between the helium and the C60. Are you going to tell people there are 60 helium carbon bonds in this molecule? This is absolutely crazy. There are not 60 helium. There's a weak interaction. And Bader knew this from the beginning, because he, even in the beginning, he had two helium atoms approaching each other, which repel each other at short distances. But he had a bond critical point. So the bond critical point is a feature of the topology of electron interactions. It is not a measure of a bond. You can restore a little bit by looking at the second derivative of the density. Bader's theory is based initially on a first derivative, the gradient in the second derivative. When this is negative, then one typically has a normal bond. When it is positive, one has a repulsion. So one can save some some aspects of this. I'll come back to what I think of Bether's theory, but you see that it's not very useful for this. There's another measure recently called ELF, or not so recently, it's a while, it's almost 30 years. ELF is an interesting measure. It's constructed in a funny way. Let me try to describe it. When somebody shows you, to find out whether a person really understands what ELF is, when someone shows you an ELF function, what you do is you plead innocence and you say, Professor, I don't know what an ELF function is. Could you tell me what it is? What you'll find is 99% of the time people don't know what it is, but they have pushed a button which calculates it, okay? So now I'll tell you what ELF is. ELF is a very clever attempt to measure those regions of space where there are electrons of opposite spin localized. So, where does a chemist think that electrons of opposite spin are localized? In bonds and in lone pairs. And, you usually don't think about it, in cores, in 1s electrons. So if you invent such a measure, that's where you should get a large value of ELF. In a core, in a bond, in a lone pair. If it's ammonia, in a region away from the nitrogen, where you think there's a lone pair, in the NH bonds, and in the 1s orbitals of the nitrogen. Okay. So they devised a measure. It turns out that it's difficult to calculate where electrons of opposite spin are. So they said, let us calculate where electrons of the same spin are. And electrons of opposite spin will not be there where the electrons of the same spin are. Okay? So that's why they put this in a denominator over there, so as to get an inverse relationship. And then they said, let us measure. Turns out that you have to go to the second derivative. It's a technical thing, to measure where the electrons of same spin are. And they compared it to an electron gas, which is a very non-chemical measure. And they devised this measure, and anyway, when it's all done, they got this measure, which is defined in this particular way that you see here, and FR is the second derivative, the curvature of the probability function of electrons of the same spin. You might think that when you invent a new measure of something, that you would test it on a molecule where people know where the things are, or think they know. Like I just mentioned ammonia, you can be sure that because this measure was invented by physicists, that they did not test it on anything chemical. So it took a chemist to do this, and Jeremy Burdett did it very shortly thereafter. So here is what ELF looks like, a certain contour of ELF for water and for ammonia. And so you see the red? That's a large value of ELF. And what you're seeing is the lone pair here and the two lone pairs of water there. And you see these large balloons? Those are the NH or the OH bonds. And they are typical of ELF, that there is a large region that doesn't make that much chemical sense. But at least generally, what is omitted here is the core region on nitrogen and oxygen. There is a large value of ELF there. It's so small in such a small region that you can't see it. So here is cyclohexane. Every organic chemist knows where their bonds in cyclohexane are. There are CC and CH bonds. So here you see them. Little small green areas, those are the CC bonds of cyclohexane. You see the large balloons, those are the CH bonds of cyclohexane. Here is cyclopropane. It's actually very nice. Look at this. Those green areas in cyclopropane are outside of the line connecting the two carbons. Every organic chemist knows there are bent bonds in cyclopropane. Here they are coming out at you. It's very nice. Here it is, but then sometimes it looks really weird. This is acetylene, in an ELF picture of acetylene. These are the two carbons. The red dots are the localized 1s regions. The balloons on the left and right are the CH bonds. And the triple bond is reduced to a single torus around. It looks, at least it reminds you that the triple bond, that the pi bond is cylindrically symmetrical, which we tend to forget sometimes. But there is no sign of a sigma bond in here. It's interesting. It's a little different. So there is a recent variant of this called electron localizability indicator, especially used by Yuri Green. It's essentially the same. This is what this indicator looks like for acetylene. You see the localization on the atoms, the CH balloons, and the CC bond, the cylindrical indicator. I can make sense of it, but it's not very chemical. So why do people buy theories? The question here is, should we believe these theories of quantum theory of atoms and molecules, or of ELF? So the usual reason that people accept theories is that the theory explains more of what is known and fits at the borders with other theories. And usually what makes people accept theories is that the theories make risky predictions. So what is a risky prediction? A risky prediction is when you take a vote among experts in the field on something that is not yet observed, and when 90% of the experts come up with the opposite of what the person has proposed. That's a risky prediction. And when that is verified, that certainly makes people believe a theory. This is what happened with Einstein's theory of general relativity and a precession of the perihelion of Mercury around 1915. It is what happened. We can point to a few experiments in the orbital symmetry story that I was involved that were of this type. But there are other reasons why people believe theories, not only these simple ones. One is aesthetic reasons. So this is very dangerous, very dangerous. People, especially physicists, tend to believe theories because they are simple. And I've already told you about presidents of the United States who believe the world is simple. And you have the analog in Spanish politicians. There is nothing special about the United States here. The world is not simple. The world is complex. And simple theories are for simple minds. So that so that's why aesthetics is dangerous. It looks pretty, it looks simple. There is another reason that people believe theories, and that is that theories tell a good story. They connect many things in something that makes sense. This is okay. It has something to do with our love as human beings for good stories. But also, in its first days, the theory of evolution, for instance, until a good part of the 20th century, the theory of evolution was believed because it told a damn good story that made more sense, the greatest story of them all. And there is another controversial reason, which my friend Evelyn Fox Keller has written about, which is social needs of a community. This is, I don't want to talk about that right now. There are two other reasons why people believe theories. One is that theories are portable. And what I mean by portable is just what it says. They're like a valise that you can take along. This is very hard for theoreticians to understand. That theory, which if you put it in the hands of a person other than you, and it turns out to be useful, is believed much more than if they have to come to you to do the calculation to believe it. That's what I mean by portable. So a theory is best believed when it is a gift. It's part of a gift economy. You give it to someone. Productive means just very simple when it's productive of experiment. Theories are believed when they suggest experiments. Not only explain, but suggest experiments. And these are other factors. And my feeling about quantum theory of atoms and molecules, it's analytical, it's descriptive, it tells you when there are bond critical points. In the 5,000 papers that use QTAAM, I have not seen a single chemical prediction. I have not seen a single molecule where it is said on the basis of the QTAM analysis that it should be stable or not stable, that it should exist, or if you should ionize it or add an electron to it, that the bond lengths will change in one way or another. It is purely a descriptive theory, and as such of, I would say, of little use to chemistry. This is a very harsh opinion. ELF is a little bit more useful. There are a few people in this world who have used ELF creative. Most people use ELF the same way they use QTAAM. They press a button, it gives a pretty graph in a paper, and they think there is a bond there. That's all that they use it for. So I don't think it's very useful either. I could talk to you about natural bond analysis, but I don't have the time really to, well, natural bond analysis is a little more chemical. It's based on a very chemical analysis. I'll say a few words about it. Frank Weinhold, it is devised to talk to chemists. It's internally, theoretically, an immensely complicated scheme. It involves a number of matrix diagonalizations, and again, it is rather hard to explain, but at the end of it, there are things that look chemical. So here is, for instance, a natural bond orbital analysis of methylamine, a rather simple molecule, methylamine, and what it gives you, this analysis, is it gives you some charges. Aha, charges. They must be calculated by some method. In this case, they come from something called a Weiberg charge. And those charges look to me a little too high, but that's a chemist's sense about it. They give hybrid orbitals, like a hybrid on carbon, a hybrid on nitrogen. They give a bonding orbital, an anti-bonding one, which look like the way the chemist thinks. So why should one believe? Why should it look like what the chemist thinks it looks like? Isn't this cyclical reasoning? Yes and no. It's okay if it comes out not looking the way the chemist thinks it's looking. But then it better have consequences of some sort, some experimental consequences. In this case, we're dealing with things we know very well. It gives lone pairs that look like lone pairs, for instance. I don't have time to talk about the energy decomposition analysis goes back to Morokuma, and especially implemented in the ADF program, and popularized very much by Gernot Franking in recent times, which takes apart the electron assay. I'm going to unfortunately skip this because I want to still make a point about something which we do know, something about which I think I want to say something about the way of analysis that we have in a way. So what I've done so far, you remember the experimental part, I didn't do justice to everything. So in the same way, I've gone at some length to molecular orbital analysis, beta electron analysis. I like the natural orbital analysis much more. It is inherently much more chemical. And the energy partitioning I haven't discussed. These are not the only ways of analyzing bonds. So what do we have at the end? We have sort of this. One guy thinks it's hexacyclohexatriene, the other guy thinks it's delocalized benzene. We have ways of talking about it. They will argue to death about it. What's different about the theoretical measures from the experimental measures is basically theoreticians are much more closer because they're not talking about real things. Maybe they are talking about little sum effects. But basically, because they're talking about things that are not real, or related to real things, and you saw how much trouble the people who talk about real things have with analyzing whether there is a bond. But the theoreticians are basically much closer to priests and politicians overall, because they're talking about spiritual things. Is there a bond here? This is more like Plato in this case, and so you have to believe like Plato, or maybe you have another worldview. But there are relations to experiment. But I want to tell you about simple molecular orbital thinking, which is what I have done for 50 years. And I want to show you how it is, on a qualitative level, how I want to defend our way of thinking about this. So here is a C2 molecule, as I mentioned. And you notice these are actually theoretical calculations here of potential energy service. But by God, I think by now we should be able to calculate C2 pretty well, and we can. So these are pretty reliable, better than the experiment on some of them. Here are the experimental bond lengths for 17 excited state, ground state, and 17 excited states of C2. If you observe the rotational spectrum, how are these obtained? They're obtained from the microwave spectrum of this, from the rotational spectrum. This is an experiment you do at the university at some level. You observe a rotational progression, J times J plus 1. You can index the states from the rotational spectrum with the theory of spectroscopy. You can get the moment of inertia of the molecule. From the moment of inertia, you can calculate the distance between the centers. So these are easily obtained experimental things. The energies are more difficult. You see the ground state is 1.23, in between, closer to a triple bond than a single bond, 1.24 rather. But you see something interesting. You see there is an excited state, triplet and a singlet, who have a bond length shorter than the ground state. Here it is. One of them, here's the other one. Isn't that interesting? Usually we think when you excite a molecule, you weaken bonds. Here is a molecule which is excited, but which has according to distance, a stronger bond, but not really. It's a weaker bond according to energy. It's a violation of Badger's rule. It mixes the definition. You also notice there is a bond, 1.53. That's this one over here. There is a bond. There is a state which has a bond length which is long. You notice the range of these things, 1.23 to 1.53? If you know anything about the structure of organic molecules, the total length of range in the total range of lengths in normal organic molecules is 1.21 for a triple bond to 1.54 for a single bond. You can get a little longer, but that's the normal range. So what you see here is the C2 molecule playing out in its ground and excited states as far as bond lengths go, the whole game of 100 million organic compounds. That's interesting. Is it an accident? No, it's not an accident. And I can give you a valence bond way of thinking about it, and you could come up with a way of thinking. It's not an accident. But how can I make sense of this? Well, it turns out that what I can do, you remember this high school, university picture of the bonding in the diatomic molecule. C2 has 8 valence electrons. So it has this filled, and then 2 electrons in here. And the ground state is a singlet. But you see that the next level is only a little higher? That's why a triplet is very close to being the ground state. That's this little thing. How close? 0.15 eV. This is very close to this, to being the ground state of this. Can we make sense of the bond lengths? This is what Mulliken did in the 1930s. Mulliken said, of course I can make sense of the ground state, of the excited states of the C2 molecule. In 1930s, he only had 7 excited states. Today we have 17 or so. And what he said is, if I take an electron from the highest filled orbital, pi u, which is very CC bonding, and if I promote it to the next unfilled orbital, that forms the triplet excited state, that I'm moving from an orbital that is very bonding to one that is a little bonding. I will weaken the bond a little. And sure enough, it weakens from 1.24 to 1.31. You put 2 electrons into that orbital, it weakens it even more. So how do you get a bond length that is shorter than the ground state? How can you possibly get a bond that is shorter than the ground state? So what you want to do is, it's obvious what you want to do. You look for any antibonding orbital. And among the 4 orbitals filled, there is a bonding and a weakly antibonding orbital. And you look for getting electrons out of there. And you promote that from weakly antibonding to weakly bonding. And that is exactly what the short bond is. It promotes from sigma u to sigma g. And how do you get a very long bond? You get a very long bond by promoting something to this orbital, which is an antibonding orbital. So Mulliken was able to make in 1939, 2 years after I was born, that was a long time ago, he was able to make sense of 6 excited states of the C2 molecule. He made risky predictions. You don't see anything like this coming from QTAIM. This is a prediction of something happening. It wasn't a prediction. It was an explanation of something that happened, but coupled to it were some predictions. And he was able to do this 78 years ago. This is what convinced people that molecular orbital theory made sense before most of you were born. And I still find it a useful and somehow a chemically consistent theory. Let me just show you something else, just to show you how you could use that theory. So here is a group of molecules that we do not teach in introductory chemistry. So what don't we teach in beginning chemistry? We don't teach anything complicated, right? Remember that contract between the teacher and student. So here are some molecules that you are very unlikely to have seen. Erbium-10, ruthenium-10, C something. Or even simpler, you are very unlikely to see dysprosium-nickel, C2. But these molecules exist. There are carbides. Of course, the most, what people usually teach you is calcium carbide, calcium C2. That has a beautiful structure of calcium 2 pluses and C2 2 minuses. C2 2 minus is isoelectronic with acetylene, so it has a triple bond length of 1.19. It's a simple rock salt array of calciums and C2s. These other ones, every one of these 20 molecules has a C2 unit in it. Sometimes they're complicated. Let me show you one of them because they are very pretty. Here is dysprosium cobalt carbide. And here is how I would explain it to an organic chemist. It's a two-dimensional layered structure, ionic, with dysprosiums here and a cobalt carbide here. And here is a top view, and the red atoms are carbon and the blue atoms are cobalt. So if I were talking to an organometallic chemist, I would say, here is a two-dimensional sheet polymer with pi bonding cobalt, ionic bonding from dysprosium to a cobalt carbide, 3 plus, 3 minus layer or 2 minus layer. And then in each layer, I have pi bonding to one cobalt and sigma bonding to another. I really don't think solid-state chemistry is different from normal chemistry. Why divide up our world? This is an organometallic sheet polymer. And if I were an organometallic chemist today, if I was starting out experimentally, I would begin to wonder, how can I solubilize this polymer? How can I create a Lewis acid, which is an alternative to dysprosium plus, which when I add it on would allow these sheets to float out. Wouldn't it be nice to have an organometallic two-dimensional polymer? So there are a few, but they're not too many. Anyway, these all have a C2 unit. The bond lengths range between 1.19 and 1.48. Is that an accident? It's the same accident that made the bond lengths form between 1.24 and 1.53 here. It's the range in bonding distances. And you can bet that the way I would analyze this is I would analyze what the inorganic counter ion here does to the C2 piece in terms of populating its molecular orbitals. And that would allow me to make sense of these bond lengths. And we have done that for these molecules. So here is my world of C2. I don't think the world is made out of C2. And we're not talking here about the nature of the bonding in it. But here is C2. I see it in the gas phase. It has a bond length range of this. I see it in organic molecules. What a travesty to reduce all organic chemistry to ethane, ethylene, and acetylene. But organic chemistry is so much richer than that. But the bond lengths are the same. Here is my colleague Pete Wolzanski has made a organometallic discrete molecule which has a C2 between two tantalums, each with an imide ligand. Here is a C2 in something made by Michael Bruce, which is attached to 4 rutheniums. Here's a C2 inside a polyhedron and a metal carbonyl and a kind of compounds which the late Paolo Chini made. Here is the C2, the calcium carbide. Here's a more complicated. Here's what happens to acetylene on a silver 100 surface. It strips off the 2 hydrogens. To me, these are all C2 and different things. You guys, not you guys, but you can call yourself a spectroscopist, organic chemist, organometallic chemist, solid state chemist, surface chemist. I think the molecules are sending you a message. Don't split up your worlds. It's one world. It's not a world. That's just, but as a theorist, I want a theory which will allow me to see these relationships. And so I come to this. So that looks, we're now at the end. We have this, remember this vague definition at the beginning, a reasonably persistent bond, connection between atoms. I'm sorry, that was not necessary. In the first hour, I gave this. Second hour, I didn't have a chance to talk about some things, but you see the theoretical version. Look, I ask you to imagine the difference between someone who says there is a bond or there is no bond, and someone who tells you that the world is complicated, and it's richer intellectually and emotionally because it's complicated. So that knowing these things about a bond, when you hit one, when you come to a bonding question, helps you sort of situate yourself. You don't have to know everything, but you should be aware of all the measures that you can have, both experimental and theoretical. So I have already given away my philosophy. I think that the person who thinks that they come up with a method tomorrow, and I fully expect some people to do that, who will tell me, yes, there is a bond, or no, there is no bond, that person has closed off all discussion, has closed off all possibility of saying something. And I think chemistry is not physics. I think the concept, even though it is central to chemistry, is incredibly interesting. So I would also ask, and I'm saying this in a self-serving way, I would ask you to remember to ask any person who tells you that they think they know there is a chemical bond and that there isn't. Ask them to make a prediction on the basis of their knowledge for how you can modify it, how you can make that bond weaker, how you can make that bond stronger. Everything that chemists are able to do. So I think we should respect chemical tradition, make the connection when we can, look for risky predictions to be sure, and just relax a little bit about whether there is a chemical bond. By some measures, you will find a bond. But the most interesting cases, by far, are just like the one that I told you for C2, where there was a bond that was shorter but weaker. That is inherently interesting and fun to understand. And chemistry is interesting. Thank you. Yes. 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 So the orbitals will change. There'll be different linear combinations, but they are the same orbitals. They will look the same in a plot. It's only when you somehow reduce the plot, the information content in a plot, that they will look different. I'll come back to another aspect of the question in just a moment. One of the ways that I test new theories, new quantum chemical programs, is I take the same molecule and I orient it. Say I were doing a calculation on acetylene. Naturally, I would orient it along one of the axes. Now, I know that the orbitals should be the same, even if I orient it not along the axes. So they will look different, the linear combinations, but the shape of the orbital, the plot should be the same. So whenever I have a new program, I immediately test it on a molecule where I've rotated the molecule, and it gives me the same orbitals. Same energy, same shape in a plot. Now it could be you are talking about something else which has been at the heart of chemistry as a question and which bothers students always and researchers, and that is, should we deal with a localized or a delocalized representation? Let me formalize the question is, are the orbitals, are there two lone pairs in water, which are both in sp cubed hybrids or something close to it? Or are there delocalized orbitals? So one picture of water, which we give to students, is there is one lone pair here and another lone pair here. That comes out of forming hybrids and then occupying them. And those two lone pairs are equivalent, both occupied. The other picture is a picture that we give students of delocalized orbitals, and that there's an orbital B2 or B1 and symmetry, and we have again two orbitals of unequal energy. And now, so there is a problem that the community has in general in dealing with these two pictures of bonding. It's not just water, it's other things. So which one is right? So here is the story. Turns out that for any property of the molecule that depends on all the occupied orbitals, that the two pictures can be transformed into each other without any loss of generality or without any change in the observable. So you are free to deal with either picture. So what is such a property? Such a property is the total energy of the molecule, the total dipole moment, the total any electrostatic moment. If you ask a question about a property of a molecule that depends on, I'm sorry, it didn't come out very distinct. I will try to write it again. If you ask the question about a property which depends on one orbital or a subset of orbitals, so what are such properties? Ionization potential, take this to infinity, a spectrum, transition from here to here. If you ask such a property, about such a property, then you can do it in either framework. But if you do it in the localized framework, you will be forced back into the delocalized picture immediately. So here's how it goes. If you were to ask to ionize the water molecule. And if you like the picture of lone pairs, then when you ionize from N1, so you get a state 1 electron in N1 and 2 electrons in N2. And immediately you realize that degenerate with that is a state where 1 electron has been ionized from the second orbit lone pair. And they are of the same energy. And then you are forced immediately in 0th order perturbation theory to take a linear combination. When you take the linear combination, you go out into this. So there is no, so that you might as well, in those cases, start out with the delocalized picture. Or to put it another way, where if you want to see lone pairs in water, it's fine to see them this way. But if you ask a question, on what orbital am I ionizing from when I ionize water? It is this orbital on that over there for the first ionization potential. So now that's pretty well understood by many people in the community, not all. The real problem is what kind of an observable is chemical reactivity? So now, when water reacts, should you use this picture or that picture? So it turns out that chemical reactivity is not an observable, and activation energy is an observable for reaction, but chemical reactivity is a somewhat vague concept. So you could ask, where will a proton approach? Or where will a base, a hydride, approach? That's a more direct observable question. So it turns out that it depends on the energy difference. We could discuss this, but when the base or the acid, there's 3 aspects of chemical reactivity: acid reactivity, base reactivity, radical reactivity. That's about most of it. Let's talk about acid and base. Let's talk about acid. An acid is H+. Where will H+ react with water? Will it come in, will the H+ come along this way, or will it come this way? Slight difference. You can use the Cambridge crystallographic data file to get an answer to that. Not for H+ reacting, but for hydrogen bonding to water. Or you won't get it for water, try in ether, because then you can see, you have trouble seeing the hydrogens in water. The answer is that it's pretty much along the lone pair directions for water or for ethers, but for thioethers it changes. You have sulfur. Turns out it's more like this. So that what this has to do is with the difference in energy of the acid and its overlap with these 2 orbitals. That's at least in my point of view. I'm sorry for the long answer, but it's a question that I think has bothered the community a lot, and so I wanted to address it. Yes. Yes. Electronegativity, again, not an observable. Not an observable. And Pauling's definition, which is where the feelings about electronegativity were there before Pauling. But Pauling gave us the first workable definition. It was a very strange definition because it's based on bond energies. Electronegativity causes great problems in the shifts of the levels, but I think they can be analyzed on perturbation theory terms. Electronegativity is the most chemical kind of property. It's not quite, there are various definitions approaching it, of course. We can have one from, as you know, from qualitative density functional theory, which leads you eventually to an approximation in terms of the definition that Mulliken gave of an average of the electron affinity and the ionization potential. It's clear, so since we also know that electron affinities are in general much smaller than ionization potentials, very roughly, electronegativity goes as the ionization potential, which is sort of interesting because it's the giving up of an electron rather than the taking of the electron. I think it's better to think of both electron affinity and ionization potential and some mixture of the two being involved in electronegativity. Yes, I do. And that discussion continues to this day. There is a discussion in Angewandte Chemie just a few years ago. I forget now the physicist who was involved, but on the chemical side, it was a very good Martin Janssen, a very good inorganic chemist. And from time to time, it especially comes from the physics community. So the interesting thing is that electronegativity as a concept is important to the physicists and is an accepted concept. So what that means is every few years, someone comes up with an absolute definition of electronegativity based on some observable. And it's usually then the debate goes in the context of electronegativity and oxidation states. So we enter another non-observable, which is an oxidation state. The electron count is an observable, but not an oxidation state as such. But there are many things that are close to it, that are measures of the oxidation state. Soon I'll wind up teaching a whole chemistry course here, yes? It's lots of fun. Chemistry is just an incredible assembly of near observables that are useful as a guide for judging chemical reactions. It's amazing, and it's beautiful, and it's complex. Yes, they are fuzzy. Thank you all. Yes, was there one question, Ernesto? Thank you. Thank you. Thank you. Yes. It's connected to many other things. So the question was about the quadruple bond in a carbon molecule, which Sasson Shaikh and his co-workers have analyzed. That is, in addition to this, they have assumed that this gives another coupling. And if this looks strange to you, that two orbitals that way should be coupled, then I would ask you to look at this molecule where I add all the hydrogens so that we are sure we know what we're talking about. This is 1,1,1-propylene. This is a real molecule. There is a crystal structure. There's all kinds of measurements on it. And it has this inverted thing, and if you think the normal hybridization arguments would lead you to think there is this, but there is a coupling of these. The coupling is weak. I have engaged in a discussion with Rzepa and Shaikh, a trialogue that we published in Argument Chimie that you can read. I think there is a quadruple bond. I think the fourth bond is very weak. Well, it's weak, 20 kilocalories is the estimate. I think I have several opinions. I think there is a quadruple bond, but I think the reactivity is clearly that of a diradical. So C2 strips the hydrogen from methane with zero activation energy. It behaves like a radical in every possible way. You do not have bottles of C2 quadruple bond, so that what bothers me about calling it a quadruple bond is because in the rest of our experience we have an association that somehow more bonds is better. Now, every organic chemist knows that that is not true, because a triple bond is less stable than a double bond, which is less stable than a single bond. In organic chemistry, triple bonds are the source of reactivity. They are the thing at the top from which you can go down to get double. Let me put it another way about double bonds. You cannot argue with thermochemistry, and it's like the Cambridge database, thermochemical and structural arguments. 3 ethylenes going to cyclohexane, a strain-free molecule. What is involved in this? I'm going to put in the hydrogen so that you can see this. What's involved in this is the conversion of 1 pi bond per ethylene into a new sigma bond. Okay? That reaction is exothermic. We're not talking about activation energies. We're not talking about entropy. We're talking about enthalpy. That reaction is exothermic by 67 kilocalories per mole. Do you need any more evidence that single bonds are more stable than double bonds? It's downhill. So multiple bonds, more bonds does not mean, yes, it means a shorter bond, but it does not necessarily mean a stronger bond. So that's the point here again. And so C4 deludes you with the idea that it has 4 bonds and therefore it should be more stable. Whereas in fact, we have all seen C2 because it's responsible for the majority of the blue color in hydrocarbon flames. It is, none of you have held a bottle of C2 because there are no bottles of C2. It polymerizes immediately to graphite with no activation energy, essentially. So that it's interesting how a molecule that can have 4 bonds can disappear. This is part of the beauty of chemistry. Thank you very much.